Hello and welcome back. We were looking at entropy and isentropic efficiencies for different devices. We will go on to a few other concepts related to entropy. So, we looked at the principle of increase of entropy, which essentially said that for an isolated system ds is greater than or equal to 0, and in general we said that ds is greater than or equal to del q by t. This is an inequality for an irreversible process, and inequalities are not very useful. We know it is greater than, we do not know how much it is. So, we can sort of convert this to an equality, this expression, by writing that ds is equal to some del q by t plus some delta s which is generated, some entropy which is generated in the process. So, in that fashion we can sort of convert it to an equality. So, what we can also see is what happens where you have for example, a process where you are trying to get work. So, how does this irreversibility affect the amount of work which you can get? So, that is something which we are going to look at the moment. So, in a reversible process we have that del q reversible is equal to t into ds, whereas in the case of an irreversible process we have that del q over here is this Tds minus this delta s. So, in the case of a reversible process this is 0 because ds is equal to del q by t, and del q reversible is equal to Tds, which is what we have written here. In the case of an irreversible process what we see is this del q is equal to this Tds minus this t into some del s generated. So, that is what we see as the heat transfer in a irreversible process. So, what we see is that if I have some point 1 to some point 2, okay, I have a process for the same change in state going from the same point 1 to the same point 2, where I have the same ds, the amount of heat I would transfer in this process here, the irreversible process here, for the same change in entropy, the amount of heat I transfer here is less in this case, because it is whatever was there in this case, same t into same ds minus some t into delta s generated. So, I would transfer less heat to go from the same point to the same initial point to the same final point, or in other words I need to transfer less to get to the same change in entropy, because there is some entropy generation in this kind of a case. So, let me apply the first law to the irreversible process. So, the first law is of the form del q is equal to du plus del w. So, for the irreversible process I have del q irreversible is equal to du plus del w irreversible. Now, this du, I have the Tds relationship I can replace this du as Tds minus Pdv So, for the reversible process what I see is this is essentially del q, and this is essentially the work done in the reversible process It is not getting me where I want. So, I can also write it in this fashion. So, the del q reversible minus del q irreversible is del w reversible minus del w irreversible, and we already found out that del q reversible minus irreversible is essentially, so if I subtract this minus this, that is equal to essentially T into delta S gen, or I can also write this as del W irreversible is equal to delta W reversible minus T into delta S generated. So, in the irreversible process, I get whatever would have been the reversible work minus this factor. So, I do not get the complete work in a irreversible process, I get whatever I would have got minus something for the same change in state. So, this term is essentially called as the lost work, because it is the work which we do not get by virtue of the fact that the process is irreversible. So, that is essentially referred to as the lost work. We can also look at one other concept over here. So, if we have a heat engine which is operating on say a Carnot cycle between some temperature T naught and some temperature of say T. The lowest temperature T naught which is usually available is the temperature of the ambient, because I need to reject heat to some device. If I want to operate in a cycle for a long time, what I can usually reject heat is to the ambient. So, the efficiency of the cycle, of course, we know if it was a Carnot cycle, then we would have the efficiency of 1 minus the heat rejected the low temperature to the heat rejected the high temperature, which would be 1 minus essentially T naught divided by T. So, if I have a cycle of this form like a Carnot cycle consists of two reversible isothermal processes and two isentropic processes. We saw that isentropic processes on a Ts diagram are essentially straight lines. So, I can have a Carnot cycle which looks something like this. So, if I have some heat reservoir at some temperature of T, I want to run a heat engine over here in a reversible cycle, and I want to give out, I need to reject some energy here, because the second law says I cannot do away with not rejecting any heat over here, and I get some amount of work. So, the question is, what is the maximum amount of work which I can get? So, the maximum amount of work I can get depends on what is this temperature T naught. For a given temperature T as a high temperature reservoir, the maximum amount of work I can get is if I run a reversible engine between this T and whatever is at T naught. So, the lower the value of T naught, the more amount of work I can get. The maximum I can get is only when I reach this T naught. So, essentially what I see is the work which I can get, I can see on a PV diagram, but what I also know from first law is cyclic integral of del W is cyclic integral of del Q. On a PV diagram, the area under the curve gives me work. On a Ts diagram, the area under the curve gives me heat, but for a cyclic process the heats and the works are the same. So, this area within this cycle is the amount of heat which is transferred, net heat which is transferred, but for a cycle it is also equal to the net work done. So, this is the amount of work which I can get, essentially is the amount of heat from the first law. Actually it is actually the heat, but from the first law this is also equal to work. This area under this is essentially the heat which I am rejecting. So, if I had a reservoir at a temperature T, out of all the energy which this has, I can extract the energy only up to this temperature T naught. I cannot extract the work or the energy which is below this temperature T naught, because I need to reject at T naught, I cannot extract it. So, what we see is, if I have some amount of energy stored at a temperature T, the amount of energy which is available for me to use is only the energy which is above some ambient or some heat rejection temperature T naught. Anything which is below it is still there, but I cannot get access to it, I cannot use it. It is like, for example, it is like a well, I cannot go deep enough to extract it out, it is still there, but it is not useful to me. So, this energy on top above this T naught is what is called as available energy, and whatever is below this T naught, it is what is called as unavailable energy. So, in this case, for example, this T naught into delta S between 1 and 4 is unavailable to me, because I cannot use it. What is available to me is above this. So, essentially T minus T naught into delta S is what I can make use of to do work. So, I had some source which had some amount of energy as say T into delta S. Out of this, this T minus T naught into delta S is available to me, T naught into delta S is not available to me. So, what I also see is that the lower the T naught is, the more energy is available to me, which means that, for example, in a cold country where the atmospheric temperature is low, I can extract more of the energy. In a hot country where, for example, this T naught is higher, I have access to only less of the energy, because I need to reject heat, and generally my temperature at which I would reject heat is linked to the ambient conditions around me. So, that is something which we see. There is also one other concept here which we call as the extent of irreversibility. But before we do that, let me also, this is in the case of a constant temperature heat source. So, what would we do if, for example, if we had a heat source which is at say constant pressure, where the temperature is changing. So, in this case also, usually the temperature of the ambient is constant, but the temperature of the heat source is changing, let us say. So, ideally what we would do is run a series of Carnot engines. For example, this could be one Carnot engine between this and this, a different Carnot engine between that and here in small bits. We discretize this out into small bits and run a series of Carnot engines. So, if I was to look at the entire plot, it would look something like this. So, here what is available is essentially this T as a function of S, that is what is initially given is this T into delta S, where T is not a constant. So, integral of T into ds is the energy which is there. Whatever is below this is still not available. So, T naught into delta S is unavailable, and this T into delta S minus this T naught into delta S is what is available, like in the previous case. Only thing is, over here it is a function of S, it is not a constant. So, I cannot just write T into delta S, I need to take the integral of t into ds in order to find out this. If I know how this t is varying as a function of s, I can integrate this. So, this is the total, this minus integral of t ds minus t naught into delta s is what is available. This is what was the total in the heat source. This is what is available, and this remains unavailable to me. So, one last concept here is what is called as the extent of irreversibility. It is essentially the work which I could have got minus the work which I get because the process is irreversible. We found out this already. This is essentially T naught into delta S generated. So, that is also called as the extent of irreversibility, denoted as I, which is what we have, which is also the maximum work. This is the maximum work which you can get, because if this was reversible, so this is maximum work which you can get minus whatever work which you actually get. So, that is another small little definition which we have over there. I will derive one small equation which is commonly used by starting from the energy equation. I will assume there is a flow in a device with a single inlet and an outlet. So, then I have this energy equation. I already assumed that m I dot equal to m E dot is equal to m dot. I did not put the sigma in front of m I dots. I have assumed one inlet and one outlet. If I assume steady state, then this is 0. Of course, I have assumed steady state here also, because I am assuming dm by dt, which is m I dot minus m E dot, is equal to 0. Therefore, m I dot is equal to m E dot is equal to m dot. This is 0. If I assume adiabatic, then this is 0. If I assume no work done, then this is 0. So, I made these assumptions already. This m dot I can take to the other side. So, this goes. I am just cancelling, taking it to the other side, dividing the 0 by m dot. So, this goes. So, essentially now I am left with this. What I can do is I can write, I can take this hi to the other side. So, then this becomes this. What I am also going to do now is assume that this is isentropic. If I assume that this is isentropic, then I can use the Tds relationships, which are essentially Tds is du plus pdv, or Tds is dh plus dh minus vdp. Let me use this expression. If I assume isentropic, this is 0, which means that dh is equal to minus vdp. This is dh. I can write this as minus vdp. V is essentially 1 by rho. I can write this as minus 1 by rho dp. If rho is a constant, or if specific volume is a constant, which means I am assuming that it is incompressible. if I assume it is incompressible, then rho is a constant. I can integrate this, which then gives me that delta H is equal to minus 1 by rho delta P. Normally for integrating, so I want to integrate this. If rho is not a constant, I cannot integrate. I need to know the relation between rho and pressure. But if I assume this is constant, rho or specific volume is constant, then I can integrate this and I get this. So what I can do is I can now put this here. So delta P is Pe minus Pi. So if I now substitute this in this expression, so this is essentially now for me minus sorry, I took this to the other side. I should have got rid of this minus sign, which I did not do. So dH is equal to VdP. So I don't have a minus. So I get 1 by rho into this, and I can take Pi to the other side. So this term is coming here. All the other terms remain. So if I rearrange it, then what I get is P1 Pi by rho which is an expression which we often see, which is called as the Bernoulli's equation, which connects the pressure terms, or the pressure head as we call it, the kinetic energy and the potential energies. This is an expression which we can use, for example, in devices like say nozzles and so on, or a diffuser or a pipe, where we know the pressures. If we know the pressures at the inlet and outlet, and we know the cross sectional areas, and we, for example, the change in potential energy is not significant, we can find out how much will be the increase in velocity if we know the pressures or so on. One of the things we should keep in mind is that we have made several assumptions in this equation over here. We assumed steady state, we assumed adiabatic, we assumed no work, we assumed isentropic, we assumed incompressible. So all of these are fairly restrictive assumptions, but on making all of these assumptions, we have also assumed that the flow is only in one direction. In this case, there is only one inlet and one outlet. That is another assumption we have made. Essentially one dimensional flow is what we are assuming. So with all of these assumptions, this is an equation which we get, which can be used for solving some problems and so on. So I think that covers more or less all of this theory portion related to entropy, which we wanted to look at. So we will look at a few problems involving entropy. We already looked at one or two in the last class. We will look at a few more in the next class. Thank you.